Now, Archimedes' claim is that the area of CEB is 1/4 of the area of BCP, this triangle, right? This one is 1/4 of that, and coincidentally, just on the other side, we could have done this one instead of that side. This one, the companion, is 1/4 of this, right? Which means the area of this one and the area of this little sliver one is 1/4 of the sum of these two, but the sum of those two is ABC, right? So by pumping out from within the triangles, erecting these triangles on the legs of this other triangle, you capture, first of all, you stay within the parabola because these are inscribed. At no stage of this iterative process do you ever step outside the parabolic segment. So you're always sneaking up on an estimate of the area of the parabolic segment from within. And every time you do that, you add 1/4 of what you just added. So if you have the base one, ABC, put these two in the hopper, that's 1/4 of ABC. Do it again, and if you can't really, it gets awfully hard to look at the drawing. There's one that goes here to here, right? And so forth. There's 4 of them next time around. And their total area would be 1/4 of the area of the two little ones, hence 1/16 of the area of ABC, right? And so forth. On you go. You have the area of ABC plus 1/4 of that, plus 1/4 of that, which is 1/16 of the original, plus 1/4 of the next one. That's a 64th of the original. You're going up by powers of 1/4. That's a geometric series, which your history book there weasels on a little. Actually, Archimedes weaseled a little bit himself. I was thinking about that, how you would prove to somebody, or at least convince them overwhelmingly, that you exhaust the area of the parabolic segment. Who's to say that you keep doing all this triangle stuff and there's some little piece over here that never gets covered? Is it obvious to you that any point that is strictly inside the parabolic segment eventually is harvested, is overlaid by some triangle by this construction? What happens is a countable number of points along the parabolic arc become inscription points for trying something. This process will not pick up every point on the parabolic arc, will it? Because you have uncountably many of those. But this process, every time you inscribe a triangle, you pick up some more points, but it's always a finite set. If you do that countably many times, you still have countably many points on the parabolic arc that are covered. But if you're strictly inside the segment, you get eaten up by a triangle at some stage of the game. And since all these triangles are inscribed, you never go outside the parabolic segment. So it's like it's inevitable. It's a monotone sequence coming up from below, and no point inside is ever spared. You can't make that statement about the entire figure because there are points on the parabolic arc themselves that are never inscription points for triangles. So what? They have area 0. That's okay. So you sneak up on this thing from inside. You never go outside. You sum the geometric series, you get 4/3, and that's the content of the theorem. So exactly why does this work again? Oh. Holy crow. Figure 13 in the text. This distance here, EF, is much less than the distance EG. That can't be true. They're even distances. So his drawing is not to scale, and that faked me out the first time. EF and EG are supposed to be the same. There are some elementary things that we can notice here. Remember that we had this nice parallelogram going for us. A lot of the argument is tied up in the parallelogram. Is it obvious to you that the triangle BHG has 1/4 of the area of the triangle BPC? There's an elementary theorem in geometry that says if you have a triangle, it doesn't have to be a right triangle, any old triangle here, I'll draw it so that it is definitely not a right triangle. And I find the midpoints of these sides and connect that. It's parallel here. The triangles are similar. Since this is half of this, the areas go as 1/4, right? So this triangle has 1/4 the area of the whole thing, right? Okay, so we have that going for us here. This being the little guy, and this being the big one. Okay, and what else can we say? This is a diagonal of a parallelogram. So this triangle has the same area as this one, right? That's true. This triangle, the skinny little one that points up to B and the skinny little one that points down to C, both have the same area. Why is that true? Their altitudes are the distances, perpendicular distances of the edges of the sides of the parallelogram from the bisector, right? Okay. This is the base of a triangle. Its altitude is the perpendicular distance from there to here, right? This is the altitude. Same altitude. This was a bisector, right? They have the same base too, don't they? So what about their areas? Same. So when you add those two areas together, it's equivalent to this taking 2 times 1 of the areas. Okay. Now what's going to prove this this theorem for us? If this is half of this, then this little triangle, the pointy one there, has half the area of this one, right? They both have the same altitude. This one has, if I can show that this is half of this, then the areas would be in the same relation, right? Which means that the sum of these two, since they're equal, would be equal to that, right? But what did we just say a minute ago about the relationship of this one to the bigger one in which it sits? It's 1/4. So if we can show that EG is half of GH, it follows immediately from the argument we just went through that this triangle in its entirety has 1/4 the area of this triangle, right? And then by extension, since we could have done it to this side as well, this triangle plus this triangle are 1/4 of this triangle plus this triangle, but that's the biggie, ABC. And it's not the end of Archimedes' argument, but it's the recursion step that we need that activates the limit argument, right? You buying this?